This video will show you how to build a neural network in a spreadsheet using just the standard features, no macros. Neural networks in computers simulate the neurons in the brain. In this neural network, we have an input layer with 2 inputs, an output layer with 1 neuron, and in between is called the hidden layer, where there are 2 neurons, H1 and H2. The weights between the AI neurons simulate the strength of the synapses gaps between brain neurons. Bias is a statistical term which means a systematic deviation from the actual value. You can think of it as an offset that is applied to each neuron. Initially, the biases are typically set to 0. The individual neurons are like cells in a spreadsheet. The values of the neurons are calculated using the weighted sum of the input from the other neurons plus the bias. If the initial calculated value of the output of the neural network is not what we want, we work backwards, over and over again, changing the weights and biases and recalculating the weighted sum of the neurons until we get close to the desired output. Neural networks are good at discerning patterns. So for this neural network, we're going to try to teach it the pattern shown here. If x1 is 0 and x2 is 0, we want the output y to be 0. If x1 is 1 and x2 is 0, we want y to be 1. If x1 is 0 and x2 is 1, we want y to be 1. And if both x1 and x2 are 1, we want y to be 0. In order to set this up, we need to assign some variables. We just went through the x input values, and y will be the desired output value. We'll be setting up weights between the neurons and a bias associated with each neuron. We're also going to be setting up a learning rate k. The learning rate determines how fast a change is made as we work backwards, resetting the weights and biases. A small value of k means we may have to go through many iterations in order to get the output value that we want. A large value of k may mean a big step change from one iteration to the next, but there may be a change in the opposite direction in the subsequent iteration. What we'd like to see is steady progress towards the output that we're looking for, not a lot of bouncing up and down. Once again, here's the network, and the neurons are going to be assigned x1 and x2 for the 2 inputs, h.1 for the hidden neuron number 1, h.2 for hidden neuron number 2, and O for the output neuron. The formulas are going to be based upon the weighted sum, that is the weight between the neurons times the input plus the bias. Another way to represent that, since we have 2 neurons in the input and hidden layers, is to take weight 1 times neuron 1 plus weight 2 times neuron 2 plus the bias. Once we calculate the weighted sum, we're going to run it through an activation function. This is the sigmoid function, and it's going to convert the weighted sum to a value between 0 and 1. This formula might look a little intimidating, but the good news is we can just plug it into our spreadsheet, and the spreadsheet will do the calculation for us. Just as a reminder, the constant E is referred to as Euler's number, and it's a constant kind of like pi, an irrational number that doesn't repeat. The cost is going to be the output activation minus the desired output value, y, and then we're going to square that. And the change in weight is going to be minus k, the learning rate, times the average of the partial derivative of the cost with respect to the weight. What that means is we want to average the rate of change of the cost over the weight for each of our input lines. And there's going to be a similar formula for the bias. We'll go through these formulas in a little bit more detail in just a moment. The neuron values, we have the input values x1 and x2, and then we're going to calculate h1.a as the activation for the h1 neuron, h2.a, and output.a. So going into a little bit more detail, the weighted sum can be represented by this formula, and the activation is represented by this formula. If we look at the activation graphically, you can see it's an S-curve where large negative values are going to be converted to 0 and large positive values are going to be converted to 1. If z is 0, it's going to be converted to 0.5. So the first calculation is going to take h1 weight 1 times x1 plus h1 weight 2 times x2 plus the bias. Then we're going to take h2 weight 1 times x1 plus h2 weight 2 times x2 plus the bias. Then we're going to take the activation of h1a and h2a to calculate the output. So the formula is going to be output weight 1 times h1a plus output weight 2 times h2a plus the output bias. Then we're going to take the weighted sum and run it through the activation, which means just substituting the proper values of A and Z. These are the formulas for calculating the change in weights. If we don't get the output that we're looking for, we're going to work backwards, adjusting the weights and biases, and then run through the process again, over and over again, until we start to get an output close to what we want. So if we work backwards, starting with the output neuron, the partial cost, the partial derivative of cost with respect to output weight 1, output weight 2, and output B. If you remember your calculus, what we want to do is take the derivative of the cost, and turns out weight 1, weight 2, and the bias aren't part of the cost formula. So we'd have to take the output activation, expand that formula. That would allow us to find Z, and we can find and expand the formula for Z. Well, that's going to get pretty complicated. So what we can do instead is use the chain rule of differentiation. And we can take the partial derivative of cost with respect to OA, then take the derivative of output A with respect to output Z, then take the partial derivative of O dot Z with respect to output weight 1, output weight 2, and output bias. I left a little space here that you'll see in a moment why I've done that. So now that we have calculated the partial derivative of cost with respect to the output weights and bias, let's do it for the hidden layer. So if we take a look at the cost with respect to H1 weight 1, we can start with the same approach that we used earlier. But once we get to output.z, we still don't have the H1 weight 1 that we're looking for. So we're going to have to do a few more calculations. And using the derivative chain rule again, we can take the partial derivative of O dot z with respect to H1a. We can then take the derivative of H1a with respect to H1z. That brings us to H1z, where we can take its derivative with respect to H1 weight 1, and that gives us what we're looking for. We'll do the same thing for H1 weight 2, H1b, H2 weight 1, H2 weight 2, and H2b. If you were to build a neural network with more than one hidden layer, you'd have to do these intermediate calculations for each of the additional layers. Okay, so let's start to solve these equations. Unfortunately, a spreadsheet can't do calculus. But the first one, the partial derivative of cost with respect to O dot A, that's pretty simple. That's going to be 2 times O dot A dot minus Y. The derivative of the activation with respect to Z, that's more complicated. The final answer can be represented in one of these two ways, and you can find online lots of explanations for how to get to that derivative. It's about a 6 or 7 step process. If we take the first formula and multiply by e to the z squared over e to the z squared, we can get to the second formula here. To take the partial derivative of OZ with respect to H1A just gives us output weight 1. And to take the partial derivative of O dot Z with respect to H2A gives us output weight 2. So we can plug those values into our formula. So we've solved for the partial derivative of cost with respect to output A. We have the formula for taking the derivative of output A with respect to output Z. That same formula applies to H1A and H2A. We just plug in different A and Z values. So let's solve this last column here. If we take the partial derivative of O dot Z with respect to weight 1, we get H1 dot A. If we take the partial derivative of Z with respect to O dot weight 2, we get H2A. And if we take the partial derivative with respect to O dot B, the value is 1. If we take the partial derivative of h1 dot z with respect to h1 weight 1, we get x1. If we take the partial derivative of h1z with respect to h1 weight 2, we get x2. And if we take it with respect to h1b, we get 1. It's going to work pretty much the same for the last formula. If we take the partial derivative of h2z with respect to h2 weight 1, we get x1. With respect to h2 weight 2, we get x2. And with respect to h2b, we get 1. So we can plug those values in. And these are all of the formulas we're going to need in our spreadsheet. Once again, we're going to plug in the formula for partial cost with respect to the partial derivative O dot A. And wherever we have the factor in yellow, we're going to plug in the formula for the derivative of A with respect to Z. You might be wondering why we're taking the average of these calculations. We're going to use the same weights and biases for each one of the 4 line items in the pattern that we want the neural network to discern. Because the x1s and x2s are different on each line item, we're going to get a different calculated output, the output dot A, and we're going to get a different cost. So we're going to take those 4 costs with respect to the weights and average them out, and then apply this formula to our next iteration and see if we come closer in our neural network. So let's go to our spreadsheet. This is the neural network that we want to create. I've color-coded it to make it easier to follow along. H1 is in green, H2 is in orange, and the output layer is in purple. I've used those same colors for the formulas, and I've also set up the headings using the same colors. You can download this blank spreadsheet from the link in the comments. The gray cells represent the input items. First, we have the pattern that we want the neural network to learn, and that is if x1 is 0 and x2 is 0, we want the output y to be 0. If x1 is 0 and x2 is 1, we want y to be 1. If x1 is 1 and x2 is 0, we want y to be 1. And if both x1 and x2 are 1, we want y to be 0. I've also set up the initial weights and biases. Typically, the weights are small random numbers close to 0. In order to make sure I can get a pretty good result in 100 iterations or less, I've set up some initial weights rather than using random numbers that might require more iterations to get the result. I'm using Apple numbers because that allows the formulas to use the column and row headers that I've set up. That'll make it a little bit easier to follow along. But the formulas are the same in Microsoft Excel and Google Sheets. So let's start off by copying the initial weights and biases. So So I'll point to that first one and then copy and paste it, and then do the same thing for H2 and the output. The H1 weighted sum is going to be the H1 weight 1 times X1 plus weight 2 times X2 plus the H1 bias. We have a similar formula for H2, where it's going to be H2 weight 1 times X1 plus weight 2 times X2 plus the H2 bias. In the case of the weighted sum for the output, we're going to use the H1 and H2 activations. So that formula is output weight 1 times the H1 activation plus output weight 2 times the H2 activation plus the output bias. The formula for the H1 activation is shown here, and that's going to be 1 divided by 1 plus, and to represent the constant E in a spreadsheet, we use the term EXP, and that's minus Z, in this case H1Z. And I can copy and paste that for the H2 and output neurons. You notice that I left column E blank initially, and that's because I'm going to replicate the output activation in this column, so it's easy to compare to the desired output Y that we want as we scroll through our spreadsheet. I'm just going to point to the output activation, and then the cost is the output activation minus Y, and the whole thing is squared. So we've now finished our forward feed, and we need to start on the backward propagation. So the formulas that we need are shown on the lower half of the screen. And the first one is pretty easy. That's going to be 2 times OA minus Y. We have the formula for the derivative of A with respect to Z. And let me be careful about the way I put this in. So that's EXP. In this case, we want the output Z. We're going to divide that by 1 plus exp. We want the output Z again. And we're going to square the whole thing. And let me double check that I have that formula in there correctly. Okay, I'm going to copy this formula and then edit it slightly. So over with the derivative of h1a with respect to h1z, I want this to be h1z. And in this case, I want the derivative to be with respect to h2z. You'll notice that we're going to repeat the factors of the partial derivative of cost with respect to OA times the derivative of OA with respect to OZ in every single formula. So I'm going to set that up using the $sign symbol, which allows us to preserve the columns. So in this case, that'll be times the derivative of the output activation with respect to Z. Before I put in the rest of the formula, let me copy this part of it. And then for the partial derivative of the cost with respect to W1, we're going to multiply that times H1A. For the partial derivative of the cost with respect to output weight 2, we're going to multiply that times H2A. And we're all set with the bias here. For the partial derivative of cost with respect to H1 weight 1, I'm going to multiply that times output weight 1 times the derivative of H1A with respect to H1Z times X1 we're going to do something similar for H1 weight 2, multiply that times output weight 1 times the derivative times X2. And then let's finish off the formula for the bias. And then finally for the cost with respect to H2 weight 1, we're going to multiply this times output weight 2 times the derivative of h2a with respect to z times x1. We'll do something similar for weight 2. And then multiply that times x2. And then for the bias, we'll multiply that times output weight 2 times the derivative of h2a with respect to z. All right, I can take this line and copy and paste it. And then I want to do the sum of the cost. I can then take the 5 lines that we've created and paste them into step 1. But we need to make a couple of changes. I want to repeat the pattern that we initially set up. So I'm going to point back to those cells, copy and paste. And then we need to modify the weights and biases based upon this change in weight formula. So we want that to be the original h1 weight 1 minus, and in this case we want to always refer to k in the same row and column, so we're going to use the $ feature. And what I'm going to do is copy that part of the formula. And then we want to multiply it times the average of the partial derivative of cost with respect to weight 1. And I can copy and paste that for weight 2 in the bias. And we want to do the same thing for H2. And in this case, we want to take the partial derivative of the cost with respect to H2 weight 1. And copy and paste that. And then we want to do the same thing for the output weight 1. So we're going to multiply that times the average of the cost with respect to output weight 1. And we can copy and paste that for weight 2 in the bias. So now that we have our formula set up for the initiation and step 1, we can copy and paste step 1 into our subsequent steps. And to make it easier on myself, I'm going to copy these 5 at a time. And now that I have 20 set up, I'm going to copy them 20 at a time. And that way we'll be able to get our 100 steps set up quite quickly. And by the time we get to step 100, you can see we're getting a pretty good answer. Not exactly what we want, but we can round up line 2 and line 3 and get the 1 we're looking for, and round down the line 1 and line 4 to get the 0 that we're looking for.